Okay, guys, so the assignment for the electrostatic, all right, interactive, when you click on that, open up the Google Doc, click on the blue link, it's going to take you to, all right, the interactive that we need to. Now, the purpose of this activity is to determine, all right, the law for the electrostatic force. So we need to specifically to try and determine the relationship, all right, between the force of attraction or repulsion between two charges and the factors that affect the force. All right, so get into the interactive, begins experimenting with the interface observed. The two charges can be dragged around the screen and centered on different little grid lines. You have a ruler that can also be dragged around. Observe how the sliders can be dragged to change the value or quantity of the charge, and then how those things change the electrostatic force. So going into the simulation, you got to click the Launch Interactive. Brings you here. We're going to open this beast thing up. So we have two charges here, Q1, Q2. Now notice as I drag this, that the arrows are always doing what? Yeah, they're going towards each other, right? So the first one, it looked like this about. And I was like, well, the arrows seem a little funky. They seem a little off. So if I try and center this guy, and I try and center this guy. Okay. God bless you. All right. Now, all right, so it says in challenge number 1, how is electrostatic force, which is this value up here, related to the magnitude of charge on the two objects, Q1 and Q2, keeping the same separation distance for all trials. Systematically alter the charges and record the force. Be systematic and purposeful, all right, with those changes, such as doubling, tripling, or quadrupling of this charge. Now, we want to keep the same separation distance for all. So you're not going to change their distance. You're only going to change, all right, this stuff here. All right, so if we have, let's pick a nice little number here. If we can get it to a solid 200. No, let's go to 300. If we can slide it, come on. Okay. So this would be my charge on Q2. So where I get this charge on Q2, all right, if this was my very first thing that I did, you would do 300 times 10 to the 6 coulombs. That's what you would have. And then on charge 1, we have 5 times 10 to the 6th coulombs. So you can type it, all right, in here. What did I just have? I had 5 times 10. Remember, how do you get the exponent feature? Control period. Wait, why is it not working? Wait, why isn't that being a pain? Why isn't it working there? Control comma works. Control period is not working on mine. Oh, that's ass. That stinks. All right, so go to, you're just going to have to use the caret symbol then for now. So what do I have? 5 times 10 to the, where's my simulation? 5 times 10 to the 6th, negative 6th. And the unit they gave us is coulombs, but you can just abbreviate it with a capital C. So I'm going to have 5 times 10 to the negative 6, capital C, for coulombs. To the negative 6 coulombs. Charge on Q2, 300 times 10 to the negative 6th coulombs. So 300 times 10 to the negative 6 coulombs. And then write down what the force is that they give us here, 0.4 newtons. So they wanted you to, in here, all right, be systematic and purposeful, all right, make systematic and purposeful changes such as doubling, tripling, quadrupling, etc. So then you guys would go, okay, and I would maybe leave charge 2 alone for a second and try and get this thing to double. That was 10, right? 10 times 10 to the negative 6. I'm leaving this as 300. What happened here? The force did what? Holy shit, it wound up doubling. So if I double the charge, I wound up doubling the force. So yeah, in your interactive, okay, or in your table, my second one for charge 1 was 10 times 10 to the negative 6th coulombs. The first one I had was 5. This one was 300 times 10 to the negative 6 coulombs, leaving it as that. And this was 0.4 newtons, and now we have 0.8 newtons. Okay, so you guys are going to continue on with that. All right, so I want you guys to continue on with that until you finish filling out the table. All right, I'm going to pause this for a second. I'm going to come back to you. Okay, so after you guys have gotten your data, all right, these are the numbers that I wound up kind of picking up and using here. All right, what I wound up doing, like in the directions had said, systematically increasing this guy while keeping one of the values the same. All right, so by doubling this to 10, we doubled the force. By tripling it from its original value, all right, we tripled the force. By increasing it by a factor of 4, right, we got it to a 1.6. By a factor of 5, by a factor of 5. And then what I did is I went back, I doubled the first value on Q1, and then I doubled the second value on Q2. 1.6 is how many times greater than 0.4? 4 times is great. So make a claim, all right, describing the relationship between these two values, or between these factors. Would you say that force is directly or indirectly related to the charges of Q1 and Q2? All right, if you don't remember, what does direct charge or directly proportional mean? Okay, so directly proportional means is one increases, the other increases. And inversely would be as one decreases, the other increases, or as one decreases, yeah, or one increases, the other decreases. They're the opposites of each other. So, yeah, you're going to basically just write, all right, whether you think it is directly proportional or indirectly proportional, and then claim with your evidence. So, like a direct thing, like, hey, since I doubled the charge on Q1, and did not change the charge on Q2, I wound up doubling the force. If I tripled the charge on Q1 without changing charge on Q2, I wound up tripling the force. So yeah, there is a direct, all right, there is a direct relationship between those two. Okay. So you guys will write something in for that one. Now what we're going to try and do here is to determine how the electrostatic force, all right, is related to the separation distance d by the, or yeah, related to the separation distance of the two charges. So keeping the magnitude of the charges the same on both objects. Conduct, all right, a systematic study, collecting data, and then determine, all right, how the separation distance is going to wind up affecting the overall force. So we want to try and center the two objects using the grid line, and then using distances that are a whole number of squares. Using a whole number that are squares. All right, so let's put this guy here. Whoa. Whoa. Wicked large. All right, I'm going to just throw this guy up to 50, and I'm going to leave this dude at 600. Now, we got to do the separation between the two objects' centers. So the center of Q1 falls on this line here. The center of Q2 falls on this line. So they're 1, 2. So they're 2, the distance would be 2 away. So my separation distance, I would write just 2. There, right now we're not using a unit here. And then just write down what you have for the force value. I got 75.6 newtons. Now you don't have to use the same values as the charges as I do. You could, leave this one of them at like 10, the other at 300, whatever. All right, but separation distance of 2. What do we have? 75.6. Was it? Yeah, 75.6. Okay, now I'm going to increase the distance between them. So I'm going to move Q2 to this guy here. Now I'm going to try and get him dead center as best I possibly can. So now between the centers, I have, right, here's the center, 1 block, 2 block, 3. So now I'm 3. So I would write separation distance 3, and I would write my new force. I have 34 newtons. All right. And now, guys, I want you to, again, continue on with that pattern. All right, I'm going to pause, and we'll come back in a second to come back and take a look. So what we should have seen was a dramatic decrease as we separated this. Now, as we separated down here, did the numbers change really that much? Not as much as they did right off the rip. There was like cut in half, and then cut in half again, and then kind of a little less than half, and then it started really not being that big of a deal at all. So what kind of relationship do you think was going on here? What kind of relationship would you guys think is going on here? All right, to make a claim describing the relationship between the force and the distance. Right? Yeah. So as one of them went up, what happened to the other value? It went down. So you're definitely looking at an inverse relationship based upon your evidence. And you can explain that as the separation distance increases, the force decreases. All right. So after you guys have made a claim here, we are going to come up with we're going to try and suggest an equation that relates the force, the two charges, and the distance in the form of, all right, the electric force is equal to K times, and K is a proportionality constant. We don't need to determine this value. It's always going to be given to us. But we need to figure out where the three variables would go, either in the numerator or denominator. So it should be consistent with your claims made in challenge 1 and 2. So I want you guys to try and figure out an equation. So one thing, guys, that was going on here with the separation distance, if you were just to kind of sketch out a short graph, all right, with the distance being down here and the force being on the y-axis. All right, when you're very, very close, when the distance between the two charges was very, very close together, you had a very large force. And then as you even went, all right, from 2 to 3 separation units, it dropped almost like half. And then it kind of drops more, and then it starts to tailor off where it's not really dropping that many. And if we could continue this, all right, what you're going to wind up getting is a graph or something that would look like this. Now, this is what we would call an exponential, all right, relationship. So as something happens, right, as this thing decreases, it's dramatically changing right off the rip, but then it starts to slowly taper off. But this is an inversely squared relationship. So it's an inverse exponential relationship. So the equation that you guys should wind up coming up with is F electric is equal to K times charge times 1 and charge Q, because They're directly related. And then they're divided out by, all right, the distance squared. That's an ugly F. Okay. And we're going to pick up here tomorrow, and we're going to talk about, all right, this stuff. So make sure you guys do me a favor, finish this and the your claims conclusion and submit that. All right, please.